Welcome to this introduction to Micronaut 2. My name is Graeme Rocher. I am the creator of a couple of pretty well-known frameworks in the Java space called Grails and Micronaut. I'm also an architect at Oracle Labs, where I work with the GraalVM team to make Micronaut better every day on native image. Before that, I've won an Oracle Groundbreaker award for my work on open source. I'm a Java champion, and I'm currently working to lead Oracle's contributions to Micronaut. Oracle began contributing directly to the Micronaut project since July, and I'm leading the team there to make Micronaut even more awesome. So do follow me on Twitter and LinkedIn. Those are the two links you can find me at. A little bit of background. We're going to look at the background that led to what Micronaut is today. We're going to do an introduction to Micronaut 2. We're going to look at GraalVM and Micronaut's relationship, and we're going to do a lot of demos. So in terms of Micronaut, when we started looking at the serverless space and the microservice space, we realized there were challenges to optimize existing Java frameworks because many of the existing frameworks and tools were not designed for low memory footprint workloads and cold starts. In comparison to technologies such as Go and Node, the Java solutions in the space were just not up to par. In terms of the microservices space, write once, run anywhere became less relevant in terms of the containerized workloads running on Kubernetes, with the container being the deployment unit. And Java and containers require special memory management, and there are significant benefits to producing native images that can lead to overall better resource utilization in a containerized environment. Looking at traditional frameworks like Spring and CDI, when we started investigating building Micronaut, they make extensive use of techniques that are pretty much bad for memory consumption and startup performance. The things like the uses of reflection, runtime bytecode generation, Classpath scanning, runtime generate proxies, and dynamic class loading. The reality of using these kind of frameworks is that because of these techniques, applications become fat pretty quickly on the Java platform, as all the reflective method handles get cached, and you have this proliferation of reflective data caches as things like Spring have their own cache, Hibernate has their own cache, Jackson, and so forth. And all of this becomes a problem when you're trying to keep memory consumption down. In general, it's a trade-off. Developers love the programming model that things like Spring and CDI provide and the productivity benefits. But because as soon as you turn these features off, then you see a massive drop in productivity. And if you think about it, what is really the value of something like Spring without auto configuration and so forth? So there's a lot of value in the way existing applications are structured, just not in the way they're implemented. What there is this relationship between lines of code and startup time and memory consumption. And this is one of the things we wanted to decouple with Micronaut when we started investigating building it back in 2017. In addition, we wanted to tackle common frameworks that every Java framework out there suffers from, things like a limited annotation API. So in Java, you have an annotation API, which you have to access annotations via reflection, so it forces you to use reflection. There's also really no way in Java to, for example, figure out meta annotations automatically, or whether an annotation exists somewhere in the class hierarchy, such as on an interface or so forth. There's also really no way to merge annotations. So it's common in Java bean space to have an annotation on both a field and a getter. So we wanted to deal with that problem, as long as with other related problems like type erasure. You have something in your source code that is a list of string. You really just want to say, give me that, find out what this list is. You don't want to have to jump through hoops of reflective data access in order to figure out generics. In general as well, reflection is quite slow, and we've seen a lot of attempted solutions to fix this problem in the Java space, from using things like cglib and ByteBuddy to generate method handles to improve invocation performance, to recent things directly in the JVM, such as method handles. In addition to that, I mentioned before, the reflective data cache proliferation problem, where you have like a bazillion different caches for different reflected data methods, for example, in Jackson, in Hibernate, in Spring, and so forth. We really wanted to move away from minimizing the amount of reflection that is being used, and eliminate things that are bad for startups, such as Classpath scanning and dynamic class loading. So you may be wondering at this point why exactly reflection is a problem. Well, it's actually pretty easy to find out today. The JDK is OpenJDK, and it's also hosted on GitHub. So you can go directly to GitHub and you can check out the source code. And if you look at the source code for java.lang.class, which is a class reference, you'll see that essentially all reflective data is initialized on first access and held in what is called soft references. So if those of you who are not aware of a soft reference is essentially only garbage collected when the JVM is running out of memory. So that's clearly a bad thing. You don't want to wait for your application to be low on memory before some of these things get GC'd, and many of them never do. And you'll find in a large Java application there is a significant amount of memory occupied simply by reflective metadata. And this has already been a problem that's already been addressed in other communities. So in the Android community, for example, ahead of time compilation is used extensively, and things like Dual Dagger, which is a reflection-free dependency injector that is limited in scope to DI, but essentially eliminates reflection. And if you look at really any Android tool out there, or framework, or library, you'll find that none of them use reflection, and there's a very good reason for that, because you don't want to use extra memory and hurt performance on a mobile device. It's a very bad thing if your mobile device, an application, is using more memory than necessary. And why is that any different on the server side? So we had a look at this and decided, well, we need to implement something that is appropriate for the server side, and that's where Micronaut comes in. So back in 2017, we started building out Micronaut. And Micronaut is essentially, by the name you might have guessed, it is a microservices and serverless focused framework, hence the branding. It is also a complete application framework for any type of application. So whether you're building command line apps, or serverless functions, or microservices, or message-driven microservices, or just swing apps, you can use Micronaut. Anything that has a static void main is fair game as far as Micronaut is concerned. And the way it's built is as a Java annotation processor, so that it hooks into your compiler and essentially computes your framework infrastructure at compilation time. So moving the work that you typically get happens in a framework like Spring at runtime into your compiler, and you can think of it as basically a supercharged version of Dagger for the server. What Micronaut actually computes is essentially at compilation time all the dependency and configuration injection. So it has a full DI container that's based on javax.inject. It'll compute all the annotation metadata, so it doesn't have to be read at runtime, such things like metro annotations and so forth. It computes as well AOP proxies, so it has full support for aspect-oriented programming and things like @transactional and so forth. We also have support for bean introspections, which essentially allow you to read properties from a given Java bean and set and get properties without using reflection. Essentially everything that makes up the framework infrastructure. You can think of these things as the building blocks of a framework and the plumbing that goes into a framework. And if your plumbing is reflection free and runtime proxy free and dynamic class loader free, then it makes a whole big amount of difference in terms of runtime memory consumption of your application and performance. So as I said, with Micronaut you can build a range of things. You can build microservices, you can build serverless applications, you can build message-driven applications with Kafka and Rabbit. You can do CLI apps or even Android apps. We have it running on Android. And you can pretty much do anything with static void main. And we currently support 3 languages, which is Java, Kotlin, and Groovy out of the box. So since Micronaut was first open sourced, or was first announced in March 2018 and then open sourced on the 28th of May 2018, it has had a massive impact on the industry at large. A number of different frameworks have copied the approach, including something called Quarkus from Red Hat, and on the Spring side, there have been massive efforts to try and catch up in terms of the performance and runtime characteristics of Micronaut. So in that sense, all users benefit. Micronaut is essentially changing the face of server-side Java and bringing excitement back to server-side Java, which was lacking in the last few years, and it's really exciting time to be a Java developer. Another important relationship to keep in mind is Micronaut and GraalVM. So if you haven't heard of GraalVM, it is a new virtual machine from Oracle that features a tool that allows you to convert Java into native machine code using ahead-of-time compilation. It also features a whole bunch of stuff such as the truffle language framework that allows polyglot interaction between languages, and they have an implementation for Python and all sorts of things, and Ruby, and it works really great with Micronaut. So the native image tool is a fantastic combination with Micronaut, and the reason they work so great together is because essentially Micronaut doesn't do any of the things that require configuration in native image. So if you use any reflection or any dynamic class loading or any runtime proxy generation, you have to configure those things with native image. But since Micronaut doesn't do any of those things, there's nothing to configure, which is great news from the developer's perspective, because you don't have to think about configuring things or debugging why something went wrong in your native image build. And once you actually have a native image, the startup time is sensational with something like 20 milliseconds and memory consumption dropping to 18 megabytes. So do check it out at graalvm.org. And yeah, like I said, Micronaut and GraalVM are a match made in heaven, and so much so that now I work at Oracle Labs and I'm working closely with the GraalVM team to make GraalVM and Micronaut an awesome combination for building applications on the server. Micronaut essentially does all that work for you at compile time, eliminating work that you would have to do otherwise to configure GraalVM. In terms of Micronaut 2, that was recently released in July, and it's a massive new release. We have a new native CLI, and the CLI is really cool because it's essentially written in Micronaut itself and computed into a native image for Windows, Linux, and Mac OS. So we have a native implementation which serves as a great example of how to build a command line interface using Micronaut and Pico CLI and compute it into a native image. It also runs as a completely serverless backend to the Micronaut launch, which I'll be talking about in a moment. Speaking of serverless, we have additional support for serverless for Azure and Google Cloud Function, and incremental compilation support for Gradle, as well as a brand new Maven plugin for Maven users that allows things like hot reload and all sorts of usability features. We also introduced servlet support, so if you're moving from legacy platforms, you can still take Micronaut and deploy it to a servlet environment, whether it be Tomcat or Jetty or whatever is your favorite servlet container. And we had the support for HTTP2, which is clearly important for the future of Micronaut, and massive improvements came to GraalVM. So there's so much more that is compatible with native image in Micronaut 2 that wasn't compatible in Micronaut 1. That's really quite seamless now. Do check out the guide on what's new. There's a whole bunch of stuff. The link is there. One of the more significant things of Micronaut 2 was the launch of Micronaut Launch, or excuse the pun. It essentially is an application generator for Micronaut that lets you generate Micronaut applications, and it's running fully serverless in the cloud and accessible from your browser or via curl. You can visit launch.micronaut.io, or I think start.micronaut.io works as well. And you can contribute to it and check out the source. It's pretty awesome. It lets you generate apps and get started quickly with Micronaut. So that's enough talk. Let me get on with some demoing and see how we go. So this is the exciting bit. So like I said, with Micronaut Launch, you can go to micronaut.io/launch. And from here, you can start building your application and choosing your features. You can see I'm using the latest version of Micronaut, which is 2.0.2, and you have the option to select whether you are a Java user, Kotlin user, or Groovy user, or Gradle or Maven, and your test framework of choice. And there's also this button where you can click and add additional features. So for example, if I wanted to include Micronaut data JDBC, I would click that button and add it, and now I have it included. And what that has, it has an effect on this diff button. So if I click the diff button, it will show you the difference that happens to the application when adding the Micronaut data feature. So if you needed to add this to an existing application, you can see how to do that. There's also a preview button where you can click and you can see what's actually going to be generated. So you can see the application .java and the build.gradle and all that business. And finally, you can click generate to generate your project. Now the cool thing, the backend for this is also running inside Micronaut CLI. So when you install that by SDKman or Homebrew or whatever, you will see that you can use the mm command to do very much the same thing. So and you can do it interactively. So I can drop in here and I can say create app example, for example, to create a new app. Now you can also do things like mn, and you can say create app example, and then you can pick features and have those completed. And there's a whole bunch of them. I'm going to choose data JDBC and create my app example. And you can cd into it, and just open it up in your favorite IDE, like for example IntelliJ. Once I've actually imported the application into my IDE, I like to go to my IntelliJ settings and actually set my text execution to be executed by IntelliJ. It actually gives me a more productive feeling. So in terms of what you have here is a regular Micronaut application. So you have an application class, which is this guy, and this is the one that lets you run the application, from your IDE, for example, debug it and so forth, directly within the IDE. You can see it starts up very quickly. And other than that, you have a resources directory where you have application.yaml configuration, and you can see, because I chose the data.jdbc feature, we have some data source configuration. You have a logback file, and you also get a test in here which allows you to just assert that the application can and does start up correctly, and as you can see, it executes extremely quickly. So what do you get with Micronaut, and what does it do? So one of the things you have in Micronaut is, typically in an application, a Java application, you have these kind of entity classes. So over here I have a person class, for example, and what you want to do in Micronaut is annotate these types of classes with @introspected. And what that allows you to do is do things like read and write the entity directly, dynamically. For example, instantiating objects dynamically and so forth, like a Java bean introspection essentially. They can be immutable, so I can define a constructor, and you can define getters and setters. So how would I use this in code if I wanted to do anything dynamic? So for example, you could go write a person test here, and you could annotate this as a JUnit5 test, and what I could do is get hold of what's called a bean introspection. So I can say bean introspection person.class and get hold of an introspection like that. Now introspections can also contain, and we have out-of-the-box support for validation, so you can go in here and say things like, this is not blank, this shouldn't be blank, and the minimum age of the person should be 18, and you can even define the mixed on the getters themselves as well. So you can say, the size of the name, the max should be 200 or something like that. Probably that's even ridiculous, person with a name that long. So that's, you can define essentially JavaX validation rules directly on the entity, and those will be available. And with the introspection, what I can do is I can instantiate an entity, so like for example Fred, like so, and then I can say assert equals Fred.getName. So I can basically dynamically instantiate objects, and the bean introspection itself is built at compilation time. So there's nothing happening at runtime that's using reflection or anything dynamic. You can also use an inspection to get a property. For example, I can get a particular property of this class, for example, a name property. I can say that is of type string, and I can, for example, read from that property here. So I can say Fred get using that person, and it will read that property automatically for me. So all that is pretty cool. So so with that, that's bean introspection. So how would these be used in a real world application? So typically with dependency injection, you may define a service, for example, a person service class, and we can annotate that as being a singleton instance. And this guy is going to return a list of person, list people, for example, like this, and it's going to be an arrays as list new person. That's going to be Fred 35, and it's going to be another person, let's call them Bob, and they're going to be 25, like that. Okay, so, and we will probably want to import that to fix that. There we go. Here we have my person service. So what would maybe you would inject this, for example, into a person controller. A controller is a web controller, for example, to expose REST endpoints, and this could map to the people endpoint, and we could inject our person service into this endpoint like so, maybe make it final, and add a constructor for that, then define a REST endpoint here that maps the root, that lists all of our people, and uses the person service to to return the result like so. So there we go. There's my controller that exposes the people endpoint with my new person service. So how would I test that? Let's write a person controller test, for example, and this is going to be a Micronaut test. Oops, Micronaut test. That's it. And it's going to inject the person. No, it's not going to inject anything. What we want to do is we want to invoke this over HTTP. So what we want to actually do is define a client that's going to invoke the person service. So I'm going to define a declarative Micronaut HTTP client, and it's going to use the client annotation to map to the people endpoint of the server. And then using pretty much the same API, in fact you could extract an interface and share them between the client and the server. I'm going to define what I want to invoke over HTTP, then I'm going to inject the person client like this, and we're going to write a test that's going to test the list people endpoint, and we're going to invoke the client, list all the people, and what I'm hoping to achieve is that at the end of the day we're going to have a 2 people back from this endpoint, and that's it. So with that, yes, we get it back. It executes, and let's look how fast that. This is a full end-to-end test. End-to-end test that's invoking over HTTP, and it executes blazingly fast. If you don't believe me, you can go into logback.xml. You can define a logger in here, for example, like a name that is IO to Micronaut HTTP client, and you can say this is going to be the trace level logging, and you can run it again, and you'll see that when I run this, you'll see the JSON HTTP client reading the JSON back from the server. There it is, coming back. So that's pretty cool, and that's pretty cool. But now, what if you wanted to involve an actual database? So when you involve a database, and I've already set up one in my application configuration, we can use something called Micronaut data. So Micronaut data supports both JPA and raw SQL. I'm going to use raw SQL, JDBC. So I'm going to define this as a mapped entity with Micronaut data, and that means it's going to be mapped to the database. And the only additional change I'm going to make here is I'm going to say that this has an ID that's a generated value. So it's going to have a private long ID like that, and it's going to have a getter and a setter. There we go. So there we have added an ID to the person. Now I'm going to transform my person service into a repository instead. So it's going to extend from CRUD repository, which is going to take as arguments the person type and the ID type, so the entity type and the ID type, in this case person and long. We need to make this into an interface instead, or it can be an abstract class as well. I'm going to make this a JDB repository that is going to use a dialect h2, this we're just going to get rid of, and instead we're going to return find all from my person service. Oh, I see that find all actually returns an iterable from the parent, so we actually have to go in here and override find all to instead return a list like that, and that should resolve that issue. Now, so how can we populate some data? So let's go back to my application class, and let's make this class in fact another bean, and inject my person service into it like so, and add a constructor parameter for it. Then we're going to add an event listener here that's going to trigger whenever startup happens. So on startup it's going to get triggered, and we're going to make it @transactional, and then we're going to use the person service to save a couple of entities. So we're going to say raise.save as list, and we're going to populate this with new person Fred 25 and another person called Bob. It's going to be like really ancient, like 60 or something, and we're going to save those 2 people on application startup. And now let's run my tests again and see what happens, and which is what we've done, and there we go. So it's passing again, and this time we get, as you can see in the response, we get the database primary keys coming back and Bob in uppercase. So we are actually using in-memory database. The only thing you need to remember to do additionally because the default server in Micronaut is based on NetEase, so we don't really want to run I/O operations on the Net event loop. So we want to switch this to the task executors, the I/O thread pool, and run those operations on a separate thread pool, which we can do so by using the execute on annotation. So how do we now take this application into production? So what you can do is use gradle-w assemble to assemble the application into a zip file and into a jar file, runnable jar, and you can just do runnable java.jar and run it like that. You can also package the application into Docker using docker build to build a Docker file, Docker image, and you can also use native image. So how do I use native image? So native image is a tool as part of GraalVM that allows you to convert the application into native machine codes. And essentially all you do is you type native image, so build, and you point to the jar file, and that will go building my native image. Now this may take some time, so we may need to edit out some of this this process, but essentially it's going to be doing all the number crunching and calculations necessary to compute this application into a native image, into a native executable that is designed specifically to run on, in this case, OS X. I'm on a Mac, so it will build a Mac-based native image. And it's going to look at, using closed world static analysis, it's going to analyze the application. And because we are essentially using, because Micronaut itself does not have any kind of reflection in it, it doesn't have any kind of dynamic class loading or anything like that, which would maybe trip up native image. This is actually a relatively simple operation as far as native image is concerned, because the application is already configured to work with native image, which is pretty cool, I think, and a good example of why Micronaut and GraalVM are such an awesome fit. So it goes through various phases. It's using what's called closed world static analysis. So that means it needs to find all the reachable parts of your code, and it's analyzing, inlining, and essentially building the image as we speak. So there you go, the native image is built, and now we can spin it up, and you can see that the application with the in-memory database and everything started up in 28 milliseconds. So that is really the power of native image, this ultra-fast startup time, super low memory footprint as well, and very cool. So that is the demo part of my presentation. In terms of where Micronaut is, it's a healthy project that is being actively developed by engineers from Object Computing, Oracle, with contributions from Google as well. We have over 257 contributors, contributions from all over the industry, 4.1k stars, 9.3k commits. Do start our repository and follow us on GitHub and show your support. Recently we set up the Micronaut Foundation, which is established to manage technical direction of the project now that there are multiple companies involved with committers on the project, from Oracle to Object Computing to Google, and it's helping ensure that Micronaut benefits from broad industry support and direction, and leading the project in the right direction. So in summary then, Micronaut and GraalVM are leading the AOT revolution. Server-side Java is adapting to this new serverless world, and building more efficient frameworks is possible right now. If you make the right framework choices, you can achieve significant cost savings in terms of cloud spend and reductions in memory consumption by using something like Micronaut. By using AOT to compute into a native image, you do sacrifice compilation speed, as you saw when I was building that native image. However, you gain a significantly smaller, lighter application that consumes significantly less memory, only 18 megabyte of memory for a Micronaut application computed with GraalVM. And going native is now a reality with native image. So exciting times to be a Java developer. Thank you very much for attending my session. Here are some additional Micronaut resources: the Git community, the user guide, Micronaut launch, the guides, Twitter, and GitHub. Thanks everybody for attending, and I hope you enjoyed this talk.